Hi guys, welcome back to my channel. My voice is feeling much better today, so I think I'm fully recovered from my cold. And today I'm going to be doing a tutorial from COMSOL on rock fracture flow. So this uses the cubic law, which I had to look up. And this is a law that talks about variably saturated flow through rock fracturing. Excuse me. So I have a master's in chemical engineering. So I did study flow, compressible and incompressible flow, but we never learned about this specific concept. So I had to look it up. But basically, the tutorial will walk us through a pattern given an aperture distribution from a text file. So it basically creates this 3D surface plot. And it looks sort of like mountains, but it would be the fracturing in between the top layer of rock and the bottom layer of rock and the water flowing through that frac. Okay, so I just wanted a little background so we understand the application of the model, but I also thought it was a little different in that it's a more complex topology and just a little more complicated, which I think is fun. So let's get started let's see if they have the geometry for this one. All right, so we're gonna start new file, model wizard, and this is a 2D model and slick physics tree, mathematics, classical, PDE. I also picked this one because I've never used the mathematics module or the mathematics physics in the COMSOL Multiphysics module. So I thought it would be an interesting application. I've always wondered like how the mathematics module works. So classical PDEs is, let's see, I'm not seeing it. Oh, there we go. Classical PDEs, so you have the little del squared, convection diffusion equation, CDEC. Here's CDEC, convection diffusion equation. Add, and the dependent variable text field, type H. Oh, up here. Okay, so generally this dialog screen or screen of the GUI, you're just selecting the physics and you're either frequency, stationary, or time dependent, but in this case there's actually a field for entry. So our dependent variable, we're changing from U to capital H. I'm assuming that's for hydraulic or head, maybe. Okay, study. Oh wait, I missed one. Click OK. I don't see an OK. In the model wizard window, click select source term quantity. And the physical quantity, why am I not seeing physical quantity? Am I missing something? Select dependent variable quantity, and type head. Filter, select dependent, and the physical, click select dependent, click select dependent variable quantity, In the physical quantity dialog box, type head in the text field. Click filter. In the tree, select transport head in meters. Click OK. In the model wizard window, click select source term quantity. Alright. In the physical quantity dialog box, type time change in pressure head in the text field and filter meters per second. Okay. In the tree, select transport time change and pressure. I did that. Okay. And then steady. In the select steady tree, select general studies stationary and done. And then I'll go ahead and save this as a flow in rock fracture. Alright, on to global definitions. In the model builder window under global definitions, click parameters 1, and in the settings for parameters, enter the following settings. So rho, or the fluid density, is going to be 1,000 kilograms per meter cubed. Standard for water. Density. Mu, the fluid dynamic viscosity, is going to be 0.001 Pascal centimeter. Now, interpolation. Define an interpolation function using the aperture data available in a file. And this is available on the COMSOL website in their application library or files library. Click function from the home menu. Global interpolation. In the settings, locate the definition. So instead of local type table, we're going to select file here and then browse for the file. So I already saved this in here ahead of time. There's a text file with describing the fracture of the rock's surface. Click import. Okay, so it imported the file. And we're going to find the function subsection in the table, enter the following settings. So this will be a function called data. And then in units, we're going to have argument 1 and 2 in millimeters. And in the function table, we've got data in units of millimeters. All right, click plot, compare with the image below. So hit the plot button, and here it's plotted the surface of the, you can imagine a layer of rock on top and a layer of rock on the bottom, and then these are all the cracks in the middle where water can seep in between and flow. So that's pretty interesting. Of all the things I've modeled so far, this is probably the most exciting. So, alright, now we're moving on to geometry. In the model builder window under component 1, click geometry 1. In the settings, locate units, and we're going to change this to millimeters. Okay, and now we're going to add a simple rectangle. So geometry, rectangle, and then our dimensions are going to be 80 wide 50 millimeters high. And in the position, we're going to start at x equals 10 millimeters and y equals 20. Field selected. Right? And now we're going to set the definition. So under component 1, right click definitions and choose variables. In the settings window for variables, locate the variables section and enter these settings. So A variable is going to be expression data arguments x and y over 1000, and it's divided by 1000 since the table units are millimeters and the SI units for COMSOL use our meters. Aperture. KS is the hydraulic conductivity. Expression A squared times rho, the density of the water, times gravity constant, which we haven't entered yet, but we will, over mu, the dynamic viscosity of the water. So that gives us the hydraulic conductivity constant. Now TS is Ks times A, so the hydraulic conductivity we just defined times aperture, and that's the transmissivity. U, velocity in the x direction. Oh, on lowercase u. Negative Ks, the hydraulic conductivity, times Hx, which we haven't defined yet, but I'm sure that will be the x component of the hydraulic head. Velocity in the x component. V is the velocity in the y component, so just the same thing, but y component of the hydraulic head gives us velocity y component. And then capital U is the total velocity magnitude, square root of u, little u, squared plus v squared, so the x and y components of the velocity vector gives us the velocity magnitude. Alright, save. And now we're going to do the convection diffusion equation. The model builder window under component 1, convection diffusion equation. Click convection diffusion equation 1. So it's going to be this first bullet here. And in the settings, locate the diffusion coefficient section. So right here. And the C text field, type T sub S, or TS. Locate the source term. And the F field, type 0. Okay, and in the damping or mass coefficient section, in the D sub A, put 0. So we've got 0 source, 0 damping. Next, define the boundary conditions. So we've got 2 Dirichlet boundary conditions, and that's it. Okay. So in the physics toolbar, click boundaries, Dirichlet boundary condition, select boundary 2 only. So that one's 3, that's 1. Okay, so the bottom boundary is 2. And in the physics toolbar, I click boundaries and choose Dirichlet boundary condition once again. Why are there 2 of those? Oh, recently used, okay. And then select boundary 3 only, so that's the top boundary. In the settings window for Dirichlet boundary conditions, or condition, locate the Dirichlet boundary conditions section. In the R text field, type 20 millimeters. Okay, 20. Why? let's see, we're only doing this for boundary condition 2. Oh, I see. Okay, so it told us at the beginning that our hydraulic head for the base, or the bottom, is going to be 0, and the hydraulic head at the top is 20 millimeters head. Let me see if I can find that in the paragraph part. Here we go. Set a hydraulic head of 20 millimeters at the upper boundary and 0 millimeters at the lower boundary. This creates a hydraulic head difference of 20 millimeters that drives the fluid flow. So, whether you're talking about fluid flow or pressure gradients or entropy, things always flow from high to low. So, high pressure to low pressure, high concentration to low concentration. So by setting a delta hydraulic head here, this is what's driving the flow through the rock fracture. We've got a higher pressure here, hydraulic head of 20 millimeters, and down here it's 0. Okay, so that was setting our Dirichlet boundary conditions. To solve the partial differential equation, so it's the second order, we need 2 boundary conditions. Now we can solve it. Compute. Oh no, before we do compute, we've got to select the mesh. The mesh 1, in the settings window for mesh, locate physics controlled and select extra fine. Okay, build all. And the home toolbar, click compute. There we go, compute. Oh, interesting. Very pretty. I like this one. Now that we have solved it or computed it, this gives us the surface plot of the hydraulic head across the rectangular cross section. So results in the settings window for 2D plot group. So we'll select 2D plot group. Type velocity 2D in the label text field. Velocity 2D. Surface 1. In the model builder window, expand the velocity 2D node. Right. Okay, surface 1. In the model builder, expand the 2D velocity node, then click surface 1. In the settings window for surface, locate the expression section and type U in the expression text field. Alright, now for the height expression, we're going to right click surface 1 and choose height expression. In the settings window for height expression, locate the expression. So right here, and from the height data list, choose expression. So instead of from parent, we're going to create a new expression entered here. Type data xy. So this was the function we defined earlier. Locate the axis section and select the scale factor checkbox. Locate the axis section. Okay. Selected the scale factor checkbox, and in that associated text field, type 1. In the velocity 2D toolbar, click plot. Alright, so now we've got this nice plot here that looks like the one in the tutorial. It's a scale factor of 1, so this is an actual representation of the physical topology. All right. Click the Zoom Extents button. Did that. Now we're going to add components. So in the model builder window, right-click the root node and choose Add Component 3D. So the root node is the very top one. Root is always like home or the base project. So right-click root, and then we're adding component 3D. All right, now geometry 2. Locate units, and we're changing to millimeters once again instead of meters. And parametric surface part PS1. And the geometry toolbar, click more primitives. So we're going to geometry up at the top, more primitives here, and we're going to add parametric surface. In the settings window for parametric surface, locate the parameter section. Okay, in the minimum field, type 10. Oh, that's the name, the S1. Okay, first parameter minimum 10, maximum 90. Second parameter minimum is 20, and maximum is 70. And look at the expression section and the X text field, type S1. Oops. So this S1 comes from here, the first parameter. We're now saying X is S1 millimeters, Y is going to be S2. Same thing here, second parameter is called S2. And in the X text field type, or in the Z text field type data, arguments S1, S2. So we've got a three-dimensional plot here where we've defined the range of X as 10 to 90, the range of Y as 20 to 70, and then Z is a function, specifically the data function of those two input arguments. Locate the advanced settings section. So down here a little bit, scroll, and the relative tolerance text field type 1, E negative 2. Okay, so we're actually loosening the tolerance a little, increasing the relative tolerance from 1 E negative 6 to 1 E negative 2. In the maximum number of knots, type 100. Okay. Click build all objects. All right, so we get this nice sort of monotone foil looking representation of the surface now, given these new parametric surface input. In the model builder window under component 2, right click definitions and choose variables. Enter the following settings. So similar to how we did earlier, we're entering settings, but now it's for a different component. So it's going to seem redundant, but oh, and this is kind of nice. So it's learning from our last table, and it auto-filled aperture because it looked familiar. That's kind of, oh, nice. So it just auto-filled the description. It's too bad it doesn't do the expression as well, but that's okay. Rho times gravity constant. Oh, we never entered. Did we enter gravity constant? I wonder if that's just a built-in from COMSOL. Yeah, we never actually entered a global variable for the gravity constant, so that must be something that's just in the libraries, the COMSOL libraries. Like a global variable. Okay, so where was I? KS, now we're doing TS, A times KS, U is the X velocity vector, H2 TX plus W squared, so the X, Y, and Z components, velocity added and then square rooted. Alright, in the home toolbar, click Add Physics. So we're going back to home, up top, Add Physics, and that'll open up our menu on the side here. In the tree, select Mathematics, PDE Interfaces. There's PDE Interfaces and Coefficient Form Boundary, PDE. Oh, lower dimensions is under coefficient form boundary. Alright, so we added that one. There you can see the whole thing. CB is in parentheses if that makes it easier to identify. Find the physics interfaces in study subsection. Okay, physics interfaces. Oh, right here. In the table, clear the solves checkbox for study 1. So in our new study, we are not including study 1 for physics interfaces. All right, click to expand the dependent variable section. And in the field text name, type H2. There is nothing there. Oh, I think I may have added it too soon. Let's delete it from over here. All right, dependent variables. Why am I not seeing it? It is nowhere to be found. Okay, mathematics, PDE interfaces, lower dimensions, coefficient form boundary. Ah, there we go. All right. So in the field name for dependent variables, we're going to type H2. That's where H2 comes from. And then enter the following settings. Click the Units tab. And just expand this a little bit. And select dependent variable quantity. Units, select dependent variable quantity, and we're going to type in, we're going to say add to component 2. Okay, there we go. Now we can close out of that dialog box, and in the model builder window under component 2, coefficient boundary, PDE, and coefficient, click coefficient form PDE 1. And the settings, locate diffusion coefficient, and in the C text field type -TS. Locate the source term in the F field, type 0, and in the damping section put 0 for D sub A. Alright. Dirichlet boundary condition. In physics toolbar, click edges. So we'll click on the physics toolbar, edges, Dirichlet boundary condition, select edge 2 only. So that's this side. And again, selecting a boundary, edge, Dirichlet boundary condition, and selecting boundary 3 only, edge 3, sorry, and then typing 20 millimeters for the hydraulic head on this side. Add study. In the home toolbar, click add study. So we'll go up here, add study. Go to add study window, find the studies subsection, and select general studies stationary. Right, find the physics interfaces and study subsection. Okay. In the table, clear the solve checkbox for CDEQ. So we're clearing this one and only keeping the new physics we've added. Click add study. Okay, so now it appears down here under component 2. We can close that box. And the home toolbar, click compute. Okay, so we've got a problem with the variable name. Feature compile equation stationary solution 2 over ST1. Error in multiphysics compilation, duplicate parameter variable name. Alright, well, I'm going to have to debug later, but we'll just use the downloadable file from COMSOL since we're almost finished here. It's just this results paragraph. So I'll just use the file that works, which basically is just using that plot to add vector arrows for the surface plot of the velocity magnitude. So you can see a 3D plot with the magnitude of flow represented as these red arrows. So we'll go to the surface plot. In the model builder window, expand the 3D plot group. So this was the 2D plot group we did before. Now we have a new 3D plot group that we just computed. Expand the 3D plot group 2 and select surface 1. In the settings window for surface, locate the expression and type U. So this would have been H default, so we're just going to put a capital U in there. In the model builder window, right click 3D plot group 2. Let's see, where is that? And choose arrow surface. Oh, okay, so they've already added it here, but in order to add an arrow surface, you just right click on the plot group and then select arrow surface from that menu. So I'm going to delete that since they've already added it here. And then for the parameters or for the expression, we go to the settings section. The arrow surface settings expression. Okay, so for the X component, type little u, Y components little v, Z components little w. Locate coloring and style, and you can customize your arrows here. So you can type arrow, arrowhead, cone, double arrow. Let's see what a cone looks like, just so I'm adding value here. So that changes the arrows to cones. Arrowhead is without the tails. Double arrow. I don't actually see any double arrows, so I don't think that changed it. Choose normalized. Let's see what logarithmic looks like. So they're much smaller for logarithmic. Proportional, they're even tinier. So normalized just makes them more visible. Locate the arrow positioning section, and from placement, choose mesh nodes. So under positioning, you can pick them at different points. Gauss points actually looks like the same as the mesh nodes. Uniform doesn't appear to change it. Uniform and anisotropic also doesn't change it. But you can customize it there and then click plot. Okay, and that's it. So this was another slightly longer one. I'm not sure how long this came out since I stopped filming a couple of times, but this was fun. I did enjoy it, and yeah, I think the more difficult ones, a clearer illustration of how powerful this tool is for visualizing data. So I hope you guys enjoyed it, and if you liked it, please like, subscribe, and comment, and let me know if you have any suggestions for the channel. Thanks. See you next time.